Find the magnetic moment of Nd3 plus ion and its ground state form. So we have to calculate for the magnetic moment of Nd3 plus ion and its ground state form. Here we are looking for two things. So before we start, we need to know the magnetic moment formula, which is mu of the J state equal G of the J state root J into bracket J plus 1 ball magneton. And we also need an expression for G, and G is going to give us 3 on 2 plus S into bracket S plus 1 minus L into bracket L plus 1 all on 2J into bracket J plus 1. So in this case, we need the value for J. The value for J and the value for S, L, and then J before we'll be able to calculate for the magnetic moment. So what element are we looking here? What element is in concern here? Nd3 plus. What's the normal electron configuration for Nd? Nd gives us xenon 4f, 6s, 4f4, and s2. So we are looking at Nd plus. That means for Nd plus, Nd3 plus, Nd is going to give out 3 electrons. So the 6s electron will go away and we'll subtract 1 from the 4f orbital, remaining 4f3. And now, before we get the value for S, L, and J, we have to draw the orbitals for the F. We have to draw the F orbital. So we are looking at F3, right? So, and the F orbital, it has 7 suborbitals. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So after we are done with this, we start numbering 3, 2, 1, 0, minus 1, minus 2, minus 3. How many electrons we have in the F orbital? We have 3. So let's start filling singly. 1, 2, 3. So now that we are done with the F orbital, we then go ahead to calculate our S. Our S is a total spin quantum number. So we know for our spin number, if we have an orbital that is single field, that means the spin quantum number contributes plus half. But in a case that we have an orbital that is paired up, meaning we have 2 electrons in the orbital, so one of the electrons is going to contribute a spin quantum number of plus half, and the other one to also contribute a spin quantum number of minus half. So we are looking at our S, which is the total sum of the spin quantum number in the orbital that is in concern. So let's come back here. We have a total of 3 orbitals that are occupied with electrons singly. That means each orbital is going to contribute a plus half spin quantum number. So our S is going to be half plus half plus half. So this one contributes plus half, and this one also contributes plus half, and this one also contributes plus half. So we can there even go ahead and say, as far as we have 3 orbitals filled singly, it's going to give us 3 by half, which is going to give us 3 on 2. That is the value for our S. So now that we have the value for our S, let's calculate for the value of L. L is going to give us the sum of the orbitals. I mean, we are going to add this one out to the orbital where we have our last electron. So our last electron is at 1. So we are going to add everything here up to 1. So it's going to give us 3 plus 2 plus 1. So 3 plus 2 plus 1. So this is going to give us 6. So we have our L value to be 6. Now that we have our L value, then we go ahead and calculate for the value of J. And J is going to contribute, J equal L plus S out to L minus S. Each of these has a role to play. So we know our L to be 6 and our S to be 3 on 2. So L plus S is going to give us 6 plus 3 on 2. And L minus S is going to give us 6 minus 3 on 2. So our G will be giving us 6 plus 3 on 2 gives us 15 on 2. And 6 minus 2 on 2 gives us 9 on 2. We've gotten our J value to be 2. J has 2 values. So looking at the F orbital, if the orbital is less than half full, then we are going to take the least value for J. But if the orbital is fully half full or more, we take the biggest value for J. What is meant by an orbital is less than half full or an orbital is fully full? Let's look at a scenario here. Assuming we have an orbital like this, and we fold it 1, 2, this orbital is less than half full. Looking at this orbital, generally it's supposed to have 6 electrons in total. So if we are up to here, we can see the orbital is half filled. What about a case that we get another electron here, then the orbital is more than half full? So when we have an orbital like this, we are going to take the largest value for J. But if we have an orbital that is less than half full, we are going to take the least value for J. So let's continue. Now that we have our J values to be 15 on 2, 9 on 2, and the orbital is less than half full, we take the least value, which is 9 on 2. So our J value now is 9 on 2. Since we've gotten our J value, we can go ahead and calculate for our G. Let me transfer the work here. So we now have our J value to be 9 on 2, our L value to be 6, and then our S value to be 3 on 2. So we can go ahead and calculate for our G. And the formula for our G is here. G equal 3 on 2, 3 on 2. So G, let me write this in right. So our G is going to give us 3 on 2 plus S, and our S is what? What the value for S? 3 on 2. So 3 on 2 into bracket 3 on 2 plus 1 plus 1 plus 1, and now minus L. L is 6 into bracket 6 plus 1, all divided by 2J, and our J value is 9 on 2 multiplied by 9 on 2 into bracket G, which is 9 on 2 plus 1. Let me punch everything on my calculator. So if you punch this on your calculator, you are going to get G value to be 0.7273. So that is our G value. Now that we know the value for our G, we can go ahead and calculate our magnetic moment for Nd3 plus ion. So we know our J value, we know our J, we know our L, we know our Ls. So let's go ahead. So magnetic moment going to give us G root of J into bracket J plus 1 Bohr magneton. So now let's substitute the values in. We are going to get our G is 0.7273 root, and our J value is 9 on 2. So 9 on 2 into bracket 9 on 2 plus 1 Bohr magneton. So punching this on your calculator is going to give us 3.6183 Bohr magneton. So that is the magnetic moment for Nd3 plus ion. The question is in twofold. We are to calculate for the magnetic moment and also the ground state form of Nd3 plus ion. So let's look at the ground state form for Nd3 plus ion. I want to keep these values here because we'll be needing them. So the ground state form for lanthanide is of the form L2s plus 1 and J. So that means we have to look at what is J, what is L, what is S. And from this example, from this problem, we've already calculated for our J, and now we know our J to be 9 on 2, and our S to be 3 on 2. So our 2s plus 1, let's look for our 2s plus 1, is going to give us 2 multiplied by 3 on 2 plus 1. And this is going to give us 4. Yes, 4. So 2 cancel 2, 3 plus 1 giving us 4. What is the value for our G? We already knew our G to be, 9 on 2. So what does L stand for? The label L. What does it stand for? We get our L from the value of L that we already calculated, which is L here equals 6. That is where we're going to get our label here. We are going to get what our label L here stands for. So we have our L from the problem. We got our L to be equal to 6. So let's start numbering 0, 1, 2, 3, 4, 5, 6. Now S, P, D, F, G, H, I. We got for L to be 6, we got our label to be I. So now we know the value for our 2s plus 1, the value for our J. Then the ground state form for Nd3 plus is going to be I. Our 2s plus 1 gives us 4, and then our J here gives us 9 on 2. Our 4s plus 1, 4, and then our J value to be 9 on 2. So that's it for this question. Find the magnetic moment of samarium 3 plus ion. Here we have to only find the magnetic moment, but when we are done, we will try looking for 8 ground state form. So let's continue. The normal electron configuration for samarium is xenon, 4f, 5d, 6s, to this 0 and then F6. And we are looking at samarium 3 plus. That means samarium is going to lose 3 electrons. So this will go away and we'll subtract 1 from this. So we get xenon 4F5. So now our interest is the 4F5. So our F orbital 4F5. We now go ahead and draw our F orbitals. You know it has 7 suborbitals. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. When we are done, we start numbering 3, 2, 1, 0, 0, minus 1, minus 2, and then minus 3. So how many electrons we have in the F orbital? 5. We start filling singly. 1, 2, 3, 4, 5. So now that we are done filling, we calculate for our S. What is our S value? Our S equal to the total spin quantum number here. We have 1, 2, 3, 4, 5. So 5, each contribute half. So 5 multiplied by half. Or you can just decide to add individual halves up to the fifth term. So this is going to give us 5 on 2, which is a plus. Then we are done with our L's. We go ahead and calculate for our L. Our L go for our L. We are going to sum these up to the last orbital that we have our electron in. So summing all these up equal 3 plus 2 plus 1 plus 0 minus 1. So we know that 1 is going to take care of 1, and we have 3 plus 2 giving us 5. So our L value here is 5. Now that we are done with L, we go ahead and calculate for our G. Our J equal L plus S up to L minus S. So our L is 5. So 5 plus S, which is 5 on 2. And then 5 minus S, which is 5 on 2. So this is going to give us 15 on 2 and 5 on 2. Our orbital is less than half full. So we are going to take the least value for J, which is now 5 on 2. 5 on 2. So now that we know the value for our S, which is 5 on 2, and then our G, which is also 5 on 2, and then our L, which is 5, we can go ahead and calculate for our G. Our G equal 3 on 2 plus S into bracket S plus 1 minus L into bracket L plus 1 all on 2G into bracket G plus 1. So now let's go ahead and substitute the values in. So we now have 3 on 2 plus S. Our S is 5 on 2. So we replace here by 5 on 2 into bracket 5 on 2 plus 1 minus our L. And our L is 5. So 5 into bracket 5 plus 1 all on G, 2G. Our G value is a 5 on 2, 5 on 2 into bracket 5 on 2 plus 1. So now if we point this on your calculator, you are going to get G value to be, let me punch it to my calculator. G value to be 0.2867. Now we have our G value. We can go ahead and calculate for the magnetic moment for samarium 3 plus. Our S is here, our J is here, our L is here, our G is here. So let's go ahead and calculate for samarium 3 plus magnetic moment. So our magnetic moment formula, the Landé formula, mu equal J square root of J into bracket J plus 1 Bohr magneton. So and this is going to give us our J value is 0.2867 root of our J. Our J here is 5 on 2. So 5 on 2 into bracket 5 on 2 plus 1. Let me put this on my calculator. I'm going to pause this video. So we are going to get 0.8451 Bohr magneton. Can you go ahead and write the ground state term for samarium 3 plus? Since we have our S value, we have our J value also to be 5 on 2. What else do we need? And the ground state term is of the form L 2S plus 1J. So now that we know the value for our S, let's calculate for our 2S plus 1. So our 2S plus 1, S is 5 on 2 plus 1. So 2 is going to take care of 2. Then we have 5 plus 1 giving us 6. So our G, we already knew our G. We know our G to be 5 on 2. So the label, how are we going to get our label? The label will come from our L value that we calculated. Don't forget this. It's somehow confusing. So we got our L calculated value to be 5. So let's start numbering from 0 to 5. 0, 1, 2, 3, 4, 5. And now S, P, D, F, G, H. So our L is at H. Then that means our label here will be H. So we bring in our label. What did we get for our 2S plus 1? 6. We got 6 for our 2S plus 1. And our J value to be 5 on 2, just represented here by 5 on 2. So this is the ground state term for samarium 3 plus ion. Let's have one more example on magnetic moment and look at another frame of question. Find the ground state form and magnetic moment of terbium 3 plus. I intentionally combine frame the question into twofold to make our work easier and to to give us a broad understanding. So for terbium, what is the normal electron configuration for terbium? We have terbium to give us xenon 4f9 6s2. We are looking at terbium 3 plus. For terbium 3 plus, we are going to get xenon 6s will go away and we subtract 1 electron from the 4f orbital, giving us 8. Now our interest is on the 4f orbital, particularly 4f orbital. Listen. So let's draw our 4f orbital suborbitals. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So our 4s of F has 7 suborbitals. So let's start numbering 3. Let me change color here. So 3, 2, 1, 0, minus 1, minus 2, minus 3. So now let's fill the orbital with the available electrons. We have 8 electrons here. So let's start filling singly. 1, 2, 3, 4, 5, 6, 7, 8. So now let's continue. Let's calculate for our S. Our S equal half plus half plus half plus half plus half plus half plus half. And we have one orbital that is paired up. So the other electron here is going to give us a contribution of angular spin, the spin quantum number of -1. 2 electron, one will give us plus half, and the other one will give us minus half. So we are going to get half by 1, 2, 3, 4, 5, 6, 7. So half plus half of the 7 sides. So we can just multiply 7 by half. And then we also have a contribution of negative half. So this is going to give us 7 on 2 minus half. Bases are the same, we add, so we have 6 on 2. And this is going to give us our final S to be 3. Now that we have value for S, let's go ahead and calculate for L. Our L is going to be, we are going to sum up to the up to the orbital that we have our last electron. You can see that we are going to add this 1, 2, 3, 4, 5, 6, 7, 8. So we'll add everything. So 3 plus 2 plus 1 plus 0 minus 1 minus 2 minus 3 up to 3 again. That is where our last electron lies. Our last electron lies on the 3 orbital. So plus 3. You can see that all these will cancel out. 2 will cancel 2, 3 will cancel 2, 0 has a contribution of nothing. So our L value is 3. So now that we know the value for our L, let's go ahead and calculate the value for our J. So our J is going to be L plus S up to L minus S. And we know our L to be 3 and our S to be 3. And here to 3 minus 3. So we are going to get 6 here and 0 here. Our orbital is more than half full. So we take the largest value for J. So in this case, our J value is going to be 6. Why? Because our orbitals are more than half full. So we take the largest value of J. So now that we know the value for our J and our S to be 3, our L2 to be 3, so we go ahead and calculate for the value of J. And the formula for J is going to be 3 on 2 plus S into bracket S plus 1 minus L into bracket L plus 1 all on 2J into bracket J plus 1. So let's proceed. This is going to give us 3 on 2 plus S value is 3, right? S is 3 here, L is 3. So we have 3 into bracket 3 plus 1, which will give us 4, minus L, which is 3 into bracket 3 plus 1, which will also give us 4, divided by 2 multiplied by J. J is 6. So 2 by 6 into bracket J plus 1, 6 plus 1 giving us 7. So let me point this on my calculator and give you an answer straightforward. So our J value is 1.5. Value for our J is 1.5. Now that we know the value for our J, which is our biggest motive to get in order to calculate the magnetic quantum, the magnetic moment. So we can go ahead, magnetic moment formula, Land's formula equals G to bracket J plus 1 Bohr magneton. Bohr magneton. So our G value is 0.5, 1.5, 1.5, all root. Our G is 6. So 6 into bracket 6 plus 1 Bohr magneton, sorry. So punching this on a calculator, we are going to get 9.7211 Bohr magneton. So that is a magnetic moment for terbium 3 plus ion. Let's go ahead and look at the ground state term for terbium. Since we know most of the values already, we know our S to be 3, our J to be 6. What else do we need? The ground state term is of the form L, 2Ls plus 1 subscript J. So let's look for our 2S plus 1. Our 2S plus 1 is going to give us 2 by 3 plus 1. 2 by 3 giving us 6 plus 1 giving us 7. So what is our J? Our J is 6. So how do we know our label? Our label always will come from the value of the calculated J. The calculated L. We calculated our L here to be 3. So our label, we are going to determine our label from that value. So we got L to be 3. So let's start numbering 0, 1, 2, 3. So 0, 1, 2, 3. So SPDF. SPDF. So our L is going to take F. So we are going to get F, our 2S plus 1 is 7. So F, our 2S plus 1 is 7. So 7. And our J value is 6. So this is a ground state form for terbium 3 plus. This is a general procedure to calculate for a ground state term of lanthanide series or any of those elements. So what you have to do is just calculate your S, look for your S value and also look for your J value by using the same procedure. Let's look at another frame of question. Calculate, what is the ground state term for a free ion with 3D configuration? In this case, we have not been given the element, but we've been told that the element or the ion is in the 3D state. It's a free ion with 3d state, meaning what remains in each d orbital is 3 electrons, and that is the valence orbital too. So what we just do is that we just go ahead and draw the d orbital. We know our d orbital to have 5 suborbitals. So let's go ahead and do that. 1, 2, 3, 4, 5. And we are looking at d3. That means we have 3 electrons in the orbital remaining. So let's go ahead and follow that. 1, 2, 3. So we are to number from 2, 1, 0, minus 1, minus 2. So what next? We look for our S value. We are to look at the ground state term of the free ion with D3 configuration. And we know that the ground state term is of the form L, 2s plus 1 and J. So that means there's a need for us to calculate for our L's and our J before we'll be able to write the ground state term for the free ion. So our L's is the total spin quantum number. We have this contributing plus half plus half plus half. So plus half by 3 is going to give us 3 on 2. So let's go ahead and look for our L value. Our L value, we are going to do the same, sum up to where our last electron is. So 2 plus 1 plus 0 is virtually going to be 3. Now we are done with L. Let's go ahead and look for our J. Our J equal L plus L's up to L minus L's. So L is 3 plus S 3 on 2. So 3 plus 3 on 2. And we have 3 minus 3 on 2. So 3 plus 3 on 2 is going to give us 9 on 2. And 3 minus 3 on 2 is going to give us 3 on 2. So we just look at the orbital like how we did it. Our orbital is less than half full, so we are going to take the least value for J. And the least value for J here is definitely 3 on 2. So our J equal 3 on 2. Let me change this marker. Our J here equal 3 on 2. You will see that we have all the terms that we need to calculate for, to write the ground state term for the free ion with D3. So we know the value for S, we know the value for J, and then what we just want to look at is our label. What is our label going to be? And always our label is going to depend on the value of L that we calculated. So with this, we know our L to be 3. So our L equal 3. So we start numbering 0, 1, 2, up to 3. So this will take S, P, S, P, D, F. This is how I used to just write. So our last orbital, we are, at F. So our label is going to be F. So let's go ahead and do that. So now we are going to get our label is F, so F. So we will look at our 2s plus, let me change another sheet. Our 2s plus 1. So 2s plus 1, our s is 3 on 2. So 2s plus 1. 2 take away of 2, this 2 take away this 2, and we have 3 plus 1. Let me do that again. So 2 plus s plus 1. So this will take care of this. We have 3 plus 1 giving us 4. So we are at F, and our 4s plus 1 is 4. So here 4. And our G is 3 on 2. So 3 on 2. This is the ground state time for a free ion with with D3 configuration. Let's look at another frame of question. In this question, we were just asked to calculate the ground state time for gadolinium. We have not been given either a plus 2 or plus 3. And we know that for lanthanide series, if we have not been given any charge, they are generally found of forming the plus 3 oxidation state. So we are going to write the ground state time in terms of plus 3 oxidation states. So now, what is the normal electron configuration for gadolinium? Gadolinium is xenon 4f 5d xenon 4f 5d. Yes, this the normal electron configuration for gadolinium. So 3 will go away. That means we will just remain with the F to the power 7, I mean F7. So let's draw the F suborbital. 1, 2, 3, 4, 5, 6. So we have 7 electrons in the F. So we have 1, 2, 3, 4, 5, 6, 7. So half fold. Our else is going to be half by 7, 7 by half, giving us 7 on 2. I'm going to speed on this. So our L value is going to give us, we are going to sum up 3, 2, 1, 0, minus 1, minus 2, minus 3. We are going to sum everything up. So at the end of the day, we have 3 plus 2 plus 1 plus 0 minus 1 minus 2 minus 3. And you will see that this and minus 3 will take off minus 3, minus 2 will take off minus 2, minus 1 will take off minus 1, 0. That means our L value is virtually 0. Now that we know our L value, we go ahead and calculate for our J. And we know our J to be equal to L plus S up to L minus S. So L is 0 plus S is 7 on 2, 7 on 2. 0 minus 7 on 2. So our orbital is half-fold, is up to half-fold or more, we take the largest value of J. So in this case, our J will give us 7 on 2. Now that we know the value the value of J and that of S to be 7 on 2, we can go ahead and calculate for our S plus 1. It's of the form 2S plus 1J. So our 2s plus 1 is going to give us 2 by 7 on 2 plus 1. And this is going to give us 8. And our J value is 7 on 2. So we just look for our label. Where are we going to get our label? Our calculated L is 0. So if our calculated L is 0, it means that let's count up to 0. So we just start from 0 and let's know where we can go. So it will definitely be at S. So now our label is S, and our 2S plus 1 is 8, and then our G is 7 on 2. So this is the ground state configuration for gadolinium. We've not been given that plus this or plus this, so we just calculated based on the plus 3 or this instead. Thank you for watching. If you like video, so kindly subscribe to my channel and for more videos like this. Thanks for watching.